Hi, my name is Davidsson and I'm a PhD student from Linköping University, Sweden. I will present my poster High-Throughput Identification of Point Defects in Silicon Carbide. Here you can see the overview of the basic idea and what I will present in this poster. First, you take defects in your material of choice and you send them to the supercomputer where you run our automatic workflow which calculates spectral lines. These spectral lines are saved in a database, and when our experimental colleagues do measurements, we can compare the spectral lines they found to the spectral lines in the database and hence identify the defect. But what are these lines that we compare? Certain defects produced zerophonal lines, which can be seen as these sharp peaks in the spectrum on the left. This spectrum is for the dye vacancy in 4H silicon carbide. On the right, you can see that this zerophonal line is the direct transition between the excited state and the ground state minimum. The intensity of this line is defined by the transition dipole moment between the excited state and the ground state orbitals. And you can see the equation at the bottom here. So that are the zerophonal lines. How do we find them for all these defects? Since we have so many defects, we have divided it into several different workflows. First, we do a screening workflow with reasonable accuracy just to estimate the zerophonal line. Next, we select defects from the screening workflow that look interesting and run into a more accurate workflow. In this workflow, not only the CPLs are calculated, but all transitions between the defect state, the valence band and the conduction band edges are calculated. Also, the charge and spin states of the defect are calculated, as well as additional properties like hyperfine coupling parameters and zero field splitting, which also can be used for identifying the defect. If something looks very interesting, we can do additional manual calculations for these defects. For the screening workflow, we need to have the defects to run. These are generated by an algorithm which systematically generates unique defects clusters consisting of vacancies, antisites and interstitials, as well as combination of these. As a first test, we tested it for intrinsic defects in 4H silicon carbide. We did single and double defects up to second nearest neighbor. This amounted to 16,000 defects. Here you can see the results of these 16,000 defects. Around 4,500 CPL lines were found, and you can see them in this plot. On the x-axis is the CPL energy, and on the y-axis is the intensity. Here one sees that the intensity follows the 1 over the CPL curve, which the TDM equation, which comes from the TDM equation presented earlier. However, this plot does not take into account the non-radiative decay, which for smaller CPLs can play a huge effect. Our next step for us is to look through this data, find potentially interesting defects and run them to the full workflow to further see if we can identify new defects. Here are the references. The first three are on the method. The fourth one describes how to calculate the intensity of the zerophonal lines. And if you have any questions, feel free to contact me. Thank you for your time.